So hello everyone. Welcome to the second session of Wednesday. So the first speaker today is going to be Sofia Tarricone, and she'll be talking about higher order finite temperature Airy kernels and an integral differential Painlevé II hierarchy. So take it away.
Okay, so thank you to the organizer, first of all, and in particular to Dan for the invitation. Hi, everybody. So, well, the title of the talk is this one. I just added this Riemann Hilbert approach because we will see that even if these objects have been already introduced in the previous talk, well, today we are going to look at them with another technique. So in particular, this Riemann Hilbert approach. And the talk is based on this joint work with Thomas Butner and Mattia Cavasso that you can find on the archive with this reference number. So the plan of the talk is actually very simple. We'll go through a brief introduction in order to introduce the objects that we want to study and the basic results that are already known about this object. And we will go through some motivation. Actually, all the motivation has already been given during the previous talk. I mean, there are many applications of the objects that we want to study in statistical mechanics and random matrix theory. And these are indeed our motivation. And then we will state our main result. And the second part of the talk is, in the second part of the talk, I will try to give you the taste of the proof of this result. In particular, I will focus on the construction of an operator-valued Riemann Hilbert problem that is the new part in this and the most challenging part in this work, since there are not too much operator-valued Riemann Hilbert problem in literature. And I thought that, well, it was a good idea to explain to everybody how that works. Okay, so let's start again with something that we already see in the previous slide, but one more time, it's not too bad. So the starting point is the Tracy Wiener formula for the Astigmatic solution of the Painlevé II equation. What do I mean with that is the following result. So let's take the Airy kernel as an operator that acts on this space at 2R plus through this kernel here. So you have this integral with the Airy function. We already see that. And well, Tracy and Wiener in 1994 proved that the freedom determinant of this operator is actually related to this nice formula to a function u that is exactly the Astigmatic solution of the Painlevé II equation. And what that does it mean that? Well, it means that it is a solution of this second order nonlinear differential equation with this prescribed boundary condition. So this result was quite nice at that time because it was one of the first results that connected the random matrix theory on the left-hand side, since as we already seen, this freedom determinant here is the edge scaling limit of the probability distribution of the largest eigenvalue in GV, and Painlevé transcendence in the right-hand side. And so, well, recently in the literature, we met some new generalization of this Airy kernel, and it was quite normal to ask for a kind of Tracy Wiener formula for this generalization of the Airy kernel. And these generalizations are called Eiger order Airy kernels. And well, essentially you take the same integral operator acting on the same space, but now you replace the Airy function with the nth Airy function. And the nth Airy function is a particular solution of this 2n order ordinary differential equation. So of course, for n equal 1, you recover the classical case, the case of the Airy kernel. Otherwise, you have this new generalization. And in particular, Cavasso, Claes, and Girotti in 2019 proved rigorously and through a Riemann Hilbert approach that the freedom determinant of these new Eiger order Airy kernels do have a Tracy Wiener formula type. And well, this time the nth random determinant is related to a function u that is a particular solution of the nth member of the homogeneous Painlevé II hierarchy with a prescribed boundary condition. So actually, this formula was already given in this other paper by Ledoucelle-Majumdar-Scherer in 2018, where the authors described through this kernel some relevant statistical quantities for a model for fermions zero temperature in an harmonic trap. And well, the only difference is that in their case, in this formula, the right-hand side here, the function in the right-hand side, solves a system of Hamiltonian's equation that for the first members actually coincide with the first members of the Painlevé II hierarchy. But this the equivalence between the standard homogeneous Painlevé II hierarchy and the Hamiltonian systems for generic n is still an open problem. By the way, so we had these results for the Eiger order Airy kernels. And well, the reason why they had these two kind of different way to write down the solution of the function u, maybe it's given by the fact that they used a very different method to keep the same formula. So let's start by Tracy Wiener. Well, Tracy Wiener in 1994 proved the result through a very algebraic method, and in some way, the method used in the paper of 2018 extended this method. And also for who was there during the talk of Alexander yesterday. So the method that Alexander explained to us yesterday, it's a sort of generalization of this method that treat also finite temperature Eiger order Airy kernels. So on the other side, we have the Riemann Hilbert approach instead. So just a few years later that Tracy and Wiener proved their result, there was this paper, but many others with that, in which the Tracy Wiener formula was proved through a Riemann Hilbert approach. And the main idea of that is to write down the kernel of our operator in this way. So with this formula, and well, the operators having this type of kernel are known to be integrable operator of IIKS type. And so there is this well-known theory that allows you to connect these operators, a Riemann Hilbert problem, matrix valued, that will be of size n+1, n+1 being this value here. And of course, they were studying just the case n = 1 because that was the case interesting in literature at that time. And so for n = 1, there is no problem. You had a 2x2 matrix valued Riemann Hilbert problem that allows you to study this operator and its random determinant, and everything goes smoothly. But of course, if you now want to study the Eiger order Airy kernels, well, for every n, you will have the n and n+1 dimensional matrix valued Riemann Hilbert problem. So the dimension of the Riemann Hilbert problem increases, and this is not good. So what Cavasso, Claes, and Girotti did in order to go over this problem was to add in some way a first step before to use Riemann Hilbert problem. And this step consists in using Fourier transformation in order to show that the Freedom determinants of Eiger order Airy kernel are actually equal to the Freedom determinants of some new operator. This new operator is always an integral operator acting on some new space, but the point is that it is always also in integrable form, but now the number here is 2 for every n. Okay, so the dependence on n, the integer, is inside these functions, and so you can associate to this integral operator a 2x2 matrix valued Riemann Hilbert problem for every n. And this is the way that they use to recover the formula that we saw in the previous slide. So in a certain way, in this talk, we are going to see how this new approach can be generalized in order to treat finite temperature Eiger order Airy kernels. So of course, as you already have understood, the object of our study will be these higher order finite temperature kernels. So they are integral operators acting on the same space. And this time through this slightly modified kernel. So you see again for every integer n, the nth Airy function. And then the integral is taken along all the real line. And you have this weight function here. And the weight function, well, we can take it as any positive strictly increasing and differentiable function with these properties, but in application, this weight function is always the Fermi factor. So let's just keep in mind that it's the Fermi factor. So these operators have the following properties. So they are trace class on their space, self-adjoint, and they satisfy these inequalities. And also we have that identity operator minus our operator is invertible on L2R plus. So already these two properties are enough to be interested into their Freedom determinants, because they told us that KT and W can define a determinantal point process. And so the Freedom determinant of that operator is a probability distribution of the largest particle in the process. But of course, the main motivation for us to study the Freedom determinant of the Eiger order finite temperature operator is the fact that they appear in many, many applications. So first of all, they appear again in this paper in order to study the same model for fermion, but this time at finite temperature. So it's the model that we saw just for the harmonic trap yesterday in the talk of Gregory. But this is not the only application. So we have also this paper of Amir Corwin and Castell, where for n equal 1, so just n equal 1, but the Freedom determinant was used to express the probability distribution of the KPZ solution with narrow wedge initial condition. And prior to that, they appeared always just for n equal 1 into this paper of Johansson in the grand canonical scaling limit of the motion or Berg-Shapiro model. And there are many other occurrences of that Freedom determinant. So these were, of course, our main motivation. And what we found is the following theorem. So we have that for any t and n in this range, the Freedom determinants here can be expressed through this formula that is just the integrated version of the formula of Tracy Wiener and Capasso-Glaise and Girotti that we saw previously. But now what happens to this U? Well, this U here, it's a solution of the nth member of an integral differential Painlevé II hierarchy with this prescribed boundary condition. So just to be clear, for this result was already known for n equal 1 and was indeed proved by Amir Corwin and Castell in 2011. And well, we saw yesterday that Alexander gives a kind of this formula through a Tracy Wiener approach, okay? So now, what about the proof of this statement? Why is not, sorry, I'm having, okay. Okay, so, well, the proof is divided in essentially 3 parts. The first part regards a manipulation that we have to do on our kernels. So I don't want to spend a lot of time on that because it's very technical, but the main ingredient to manipulate this finite temperature Eiger order Airy kernel is to use this property of the nth Airy function. That is the fact that it admits a counter-integral representation. So this means that for every n, you can write it down your nth Airy function in these 2 ways, where you see, well, Cn is just a polynomial that is written here. And gamma alpha and gamma beta are some arbitrary curves in the upper complex plane and in the lower complex plane. And you just have to require that their asymptotic behavior stays respectively in this red zone and in this blue zone. So for example, if you take, well, these 2 parallel lines to the real line that are contained in the red zone and in the blue zone, that's okay. So with that in mind, well, what can be proven about our freedom determinants is the following fact. The freedom determinant of the Eiger order finite temperature Airy kernel are rewritten as freedom determinant of some new kernels that we denoted CTN. Now, CTN is an integral operator that acts on some new space, L2 sigma, and now sigma is given by this union of disjoint lines, so gamma alpha and gamma beta that we already saw, and the real line. We just asked this the technical requirement that gamma alpha and gamma beta are not too far from the real line. And well, the point is that this computation is very explicit. So this integral operator has a very explicit kernel that is written in this following way. So now, if you remember the form that had integrable operator of IIKS type, you will allow me to say that this is an infinite dimensional version of an integrable operator of IIKS type. Indeed, instead of having just a summation symbol here in front of, instead of the integration symbol, you have now this integration against the real line and with this probability measure in the right-hand side here, okay? So, well, they are not integrable operator, but they have in some way their structure. So, and the difference is in their treatment is the fact that instead of having a standard matrix valued Riemann Hilbert problem that is associated to the study of this operator, well, we will have an operator valued Riemann Hilbert problem. So, of course, as I told you, this is very explicit. This is very explicit computation is based only basically on the use of the Fourier transform. So this function Ki, Mi are very explicit, and they just depend on the curves gamma alpha and gamma beta and the Cn function that was the polynomial we saw just before. So before to go and to state who is the Riemann Hilbert problem, well, since it is an operator valued Riemann Hilbert problem, I have to tell you in which operatorial space we are going to look for the solution, and we are going to define this Riemann Hilbert problem. So to do that, I will introduce some notation. So HP will be this direct sum of Hilbert spaces, and I of HP will denote the space of Hilbert-Schmidt operator that acts on the space HP with a kernel that has to stay in this functional space. And for P equal 2, well, I of H2 will be exactly the space where we are going to define the Riemann Hilbert problem and look for the solution of that Riemann Hilbert problem. Now, in order to construct a Riemann Hilbert problem, you need a contour, and this contour will be just our sigma, the union of the disjoint line we saw before. And also you need a jump matrix that will define the jump along this contour. And well, this time the matrix will be operator valued, and it's constructed through these operators here. So who are these operators? Well, Mi tensor Kj is rank 1 integral operators that depends parametrically on zeta, the complex parameter that go on sigma. And well, it acts on L2R through this kernel here. So you just take the little Mi times the little Kj function that we saw in the previous slides. You define this function that depends parametrically on zeta and on xy, and this will be the kernel that is used by this operator to act on H1. So remark that since gamma alpha and gamma beta were these two parallel lines that were disjoint, of course, well, we have that by the definition of the functions little mi and little kj, well, m1 tensor k1 and m2 tensor k2 are 0. So now we are ready to state the Riemann Hilbert problem. And the Riemann Hilbert problem we are interested in looks as follows. So Of course, for any value of t and n, that will be our parameters in the problem, we want to determine this x, that is an operator on H2 that depends parametrically on t and n and on the complex parameter zeta, and that satisfies the following requirements. So first of all, we want this x to be analytic and away from the counter sigma. So in particular, we want to be able to write our operator x as the identity operator on H2 plus some operator x0 that will be in this space, the space of Hilbert-Schmidt operator acting on H2 with a kernel that is analytic for every value of zeta that is away from the contour. So this means essentially that if you consider for any, the function that associates zeta to x0 of zeta xy, this should be an analytic function for every fixed x and y. So this is the first requirement. And the second one, well, it describes what happened along the contour sigma, as always in the Riemann Hilbert problems. So along the contour sigma, we will have a jump condition that should be satisfied by the continuous boundary values of this operator x. So we will denote the x plus minus, the boundary values from the left and from the right respectively of the contour sigma. And well, these two boundary values should be related to this equation. And here now, this is an operator equation, and G is the operator that depends parametrically on zeta, written in this way. So we have the identity on H2 plus this operator, in which you see every entry is actually described by the rank 1 operators acting on H1 that we defined just before. So I recall you that actually this diagonal is 0. So these two are the 0 operator. And finally, the last condition that you always require in the Riemann Hilbert problem is that your solution X should be normalized to the identity while you take your complex parameter going to infinity. And well, now if you look at these three conditions and you are used to use Riemann Hilbert problem, well, you will see that these are really the same condition that you have in a standard case of matrix valued Riemann Hilbert problem, just in an operator valued case. And moreover, the construction of the matrix function that, the jump matrix here is really very similar to the jump matrix that you have in the Riemann Hilbert problem, matrix valued associated to the classical integrable operators of IIKS type. So now this operator valued Riemann Hilbert problem has not too much history. So one of the challenge of the paper was to describe that this Riemann Hilbert problem do have a solution that is unique and so on. And well, this is true. So we have that whether the Riemann Hilbert problem is solvable, it is uniquely solvable. And moreover, you have that for every Tn, the parameters in this range, well, we can write the solution of our Riemann Hilbert problem through an integral representation. So you have that your solution looks like that. You have the identity operator on H2 plus this operator valued Cauchy transform. And of course, this for every zeta that is away from the contour. Now, the operators Ni that are defined inside this solution are given in the following way. So Ni are multiplication operators on the space H1 that multiply by the functions little ni that are determined through this integral equation, where mi are the function that we define in the very definition of the operator Ctn. Now, this is just the real adjoint of Ctn. And well, this integral equation actually have solution as solution. So this function Ni actually exists because we proved in the very beginning that the identity operator minus the Eiger order finite temperature Airy kernel were invertible operators on L2R plus. And so since they shared their Freedom determinant with the Freedom determinant of CTN, well, we know that this integral equation do have a solution, and that have a solution. And so this solution actually exists. And finally, you have this last property. Of course, your solution X is invertible, and its inverse can be represented through an integral representation that it's very similar to this one. So that's it. We have a solution. What do you do with this solution of the Riemann Hilbert problem? So the first thing that you do, as it is the case indeed in the matrix valued case, well, you look at the asymptotic representation of X, because this is the way you will get then to the Lax pair of the integrable equation that you want to look at. So what does it mean? Well, it means essentially that you replace this formula in your integral representation of the solution X, and you get that, well, for every K, you can represent X in this way, where now Xj here, the asymptotic coefficients, are no longer depending on the complex parameter zeta. They are operators on H2 that takes for every entry ML this form. Okay, and in particular, as it always is the case in the matrix valued case, we will be focused on the first asymptotic coefficient, X1. Okay, so in particular, we defined these two operators on H1 that are U and V that do not depend on the complex parameter as the off-diagonal entries of the first asymptotic coefficient of X, so X1, 1, 2, and X1, 2, 1. And these two operators acting on H1, well, they have kernels with this symmetry property. So they are related to this equation, and moreover, they both are Y independent. And this will be very, very useful in the second part of the talk. So that's it for all the properties of the Riemann Hilbert problem that you have. And what do you do with this solution of the Riemann Hilbert problem? Well, in order to achieve our result, you go through two other steps that are very classical. So from one side, you want to use this solution of the Riemann Hilbert problem to deduce a Lax pair, to construct the solution of a Lax pair. So in particular, you have that this N and this M that are just the vector valued operators constructed by the Ni and Mi multiplication operators that we saw previously. They are related through this equation to the solution of your Riemann Hilbert problem. And exploiting this relation, you can prove that N here solves two differential equations, one with respect to the complex parameter zeta and one with respect to the deformation parameter t. And this is our operator valued Lax pair. And what does it mean? That, well, it means that if you consider the compatibility condition of this system, well, you will get a coupled system of ODEs that are solved by U and V, the operators that we just defined. And if you look at this equation from the point of view of the kernels of these operators, well, you will be able to see the nth integral differential Painlevé II equation for the kernel of U and V. Okay, so this is one side. The other side is to recover a formula for the Freedom determinant, because I recall you that we want to study this Freedom determinants, D and T. And well, the way you study them using the solution of the Riemann Hilbert problem is very similar to the way you use in the matrix valued case. So essentially you use this representation of D and T, and you use the fact that CTN indeed determines the solution of the Riemann Hilbert problem X, and through the integral equation that CTN that were in which CTN is involved in order to define the solution, well, you will be able to recover this formula. Okay, so just to have a look at what does it look like, the operator valued lax pair. Well, you have that these two equations have coefficients that are very simple. So in particular, B of zeta is an operator valued polynomial in zeta of degree 1. So you have zeta B0 plus B1. B0 and B1, of course, are always operator on H2, and you can write their kernel in this way. So they are B0, actually, here there is delta function, so it's a sort of multiplication operator by a constant. And B1 instead acts to this kernel here, where uxy and bxy are the kernel of the function that we saw just before. And well, A instead is always a polynomial in zeta, but this time of degree 2n. And well, you can write down the leading coefficient and the constant coefficient in explicit way, and their kernel are written just here. So this is just to say that for who already have seen the Painlevé II hierarchy and knows that the Painlevé II hierarchy has an isomonodromic lax pair, well, the form of this lax pair really is similar to the form that the isomonodromic lax pair for the standard Painlevé II hierarchy has in the homogeneous case. Okay, so the point is that, as I told you, the compatibility condition that is obtained by cross-differentiating that system, it really encodes the integral differential Painlevé II hierarchy. And to see that, well, you write down your condition and you exploit the polynomiality of B and A in zeta. And when you do that, well, you will achieve that this system is actually equivalent to a system of differential and difference equations for the coefficients AK. And this system can be solved in terms of U and B, the two operators defined before, and their T derivative. And finally, you are just left with this coupled system of ODEs that just involves U and B and their T derivatives. And well, now you define this little function, this function little u, that just depends on T and X. And well, it is defined as the kernel of U that does not depend on Y. So you have this chain of equalities, and this will be indeed the function that solves the integral differential Painlevé II hierarchy. In particular, this coupled system of ODEs, or for U and V, the operators, when you look at them at the level of the kernel, where it can be written in a very compact form, that is this one. So in the left-hand side, you just have T plus X multiplying your function, UTX. The right-hand side, you have a recursion operator, LU plus, composed with LU minus, iterated to the power n, and applied to the function u. And this will be our nth member of the integral differential Painlevé II hierarchy. So now this recursion operator, LU plus, LU minus, are defined in this way. That seems very compact and complicated, but it's not too much. So let's take a look to L minus, for example. Well, LU minus will always take some differential operator of U actually, but let's say that it acts on any function f that depends on Tx. Well, the action is defined as follows. First of all, you have this first term, you take the T derivative with respect to T, and then you have the second term to compute. And the second term is computed as follows. So first, you compute this bracket here, UF, and this bracket here gives you a rank 2 integral operator with a kernel that is defined through an anticommutator relation. So the anticommutator relation is here. So you have this function that depends on t, x, and y. That is the kernel of this operator. You integrate with respect to t this kernel, and then you compute the integral of this integrated kernel against u with respect to the probability measure w prime of x dx. Okay, so actually you see these integration terms. Well, we proved that all these expressions are local, but in order to write down these operators in a compact way, we left this integration symbol. By the way, if you go ahead with this computation, well, you will see the first members of the hierarchy appearing. And well, for n equal 1, you have exactly the equation that Alexander showed us yesterday. And for n equal 2, well, this is the same, apart from this sign here. And then you have n equal 3, this sixth order integral differential equation with respect to for u. So of course, the prime here is the derivation with respect to the parameter t, and the bracket denotes the integration along R against the probability measure w prime of x dx. So if you take w prime of x being the delta function in 0, well, all these equations actually coincide with the Painlevé II equation and its Eiger order, the classical one, for the function ut0. Okay, and moreover, the recursion operator LU plus LU minus, if you take this choice of the weight, well, it's really similar to the recursion operator that was used by Airy in 1979, that was the first to define the Eiger order Painlevé II equations. Okay, so these are the equations of the hierarchy. And well, the last thing that you have to do is to recover this formula for the logarithmic derivative of Freedom determinant. And this is done in a straightforward way. So you have first to compute the first derivative. And while you use the fact that your dnt is represented through the Freedom determinant of Ctn, use the Jacobi formula, and you express these logarithmic derivatives to this trace. And now you use the fact that, well, this derivative is explicitly computed, and this 1 minus Ctn minus 1 appeared in the integral equation for finding the solution of the Riemann Hilbert problem. So this means that finally, this logarithmic derivative can be expressed in terms of some quantities related to the Riemann Hilbert, the solution of the Riemann Hilbert problem itself. So in particular, it can be written in terms of the 1-1 entry of the first asymptotic coefficient of the Riemann Hilbert problem. That is this integral along sigma of this n1 tensor k1. And now you go for the second derivative. And so, of course, you want to compute the derivative with respect to t of this operator. And well, this is given by a formula that is very standard in integrable system to recover when you have Lax pairs, and in particular polynomials one. And the point is that this gives you exactly the derivative that you want in terms of other quantities of the Riemann Hilbert problem. And in particular, so you have this formula, and you see that if you split the integration against the eta dxi, well, the first term is exactly the operator u, and the second integral is exactly the operator v. So you end up with this formula that I told you before, and now you just compute this trace. This trace is given by this double integral. U and v have these kernels, and well, now you use the symmetry property of u and v, and the fact that w prime y dy is a probability measure. And this will give you that the second derivative of the logarithm of the Freedom determinants of the Eiger order finite temperature kernels is simply expressed through this integral. And well, in the integrated version of this formula is the formula that I showed you in the slide with the statement. So now, of course, we already proved that U was a solution of the nth member of the integral Painlevé II of the integral differential Painlevé II hierarchy. And what we have to prove is the asymptotic at plus infinity, but this is kind of easy to obtain just by using the definition of this function UTX, and then using a kind of Smolder theorem for this operator valued case that allows us to say that this integral here looks like this one, and now M1, K2 are explicit functions, and if you compute this integral, well, this is exactly the nth Airy function computed in t plus x. Okay, so we do have all the parts that we needed to prove our result, and that's it. So just about why we think that this is very nice and can be useful for the future. So in the classical case, for the zero temperature case, Riemann Hilbert approach is very useful in order to compute large gap asymptotics of the relevant Fredholm determinants. Okay, you use the nonlinear steepest descent method, and you can get these asymptotics at t going to minus infinity that are very much harder than the asymptotic at plus infinity. And well, we didn't do anything about that for the moment, but the question is, maybe with this new Riemann Hilbert operator valued approach, we can find a way to study large gap asymptotics for this Fredholm determinants, DNT. And the other point is not a question, is more a remark. So this operator valued Riemann Hilbert problem can be used anytime that you have operators like our CTN, so operators that have that type of kernel, and not just for the particular CTN with the particular choice of MI and KI. And general theory is studied by Thomas, that I think that is going to publish very soon a paper on this general theory. And the point is that, well, this theory can be applied then to study other integral operators, other finite temperature integral operators maybe, and to derive new connection with integrable system. And that's it. So thank you very much for the attention.